fantastic introduction. It's also a very nice link with Bill Shepard asking a question. He's from Soleil, and Elke has been studying in Leuven in Belgium, and then went to Soleil and is now at the IBS in France, in Grenoble. And when they did their programming of the software she's going to show, Xtrapol8, there was a bit of a curiosity seeing whether you're using calculated structures to compare with in resolving electron density for these transitions. But she was going to tell us how they do it and why it's a really good software.
I was wondering, can you see the mouse? Not really. That's annoying. Good. Okay. Good morning. So I am Elke De Zitter from the IBS in Grenoble, and I will tell you about Xtrapol8, which is a tool to identify and model low-occupancy states in macromolecular crystallography. So these low-occupancy states in crystallography, they can happen because of several reasons. So you could have done specific crystal preparation. You are maybe doing time-resolved crystallography. You may want to study radiation damage, or you're interested to know how your weak affinity ligand is binding to your protein. And so, do I get them? Great. So, in this theoretical Pac-Man example, we actually want to know the structure of our green eating Pac-Man, but unfortunately, most of the crystal is occupied by our non-eating Pac-Man. And so since crystallography is this ensemble-based method, what you will end up is with a structure which is of the non-eating Pac-Man. So this makes lives of crystallographers pretty hard because we really want to know the structure of our eating Pac-Man. And one of the tools that you can use to get to that structure of this low occupancy state is via Xtrapol8. Now, before I go into the details of Xtrapol8, I will explain something about the main examples and terminology that I will use. So when we say something about the reference state, then I refer to the state which is the most abundant one in the crystal. So mainly, this is a state of which we do not want to get the structure with our time-resolved or any other kind of experiment. Then I refer to the triggered state as this low occupancy state. So in the Pac-Man example, this is the eating Pac-Man. Then I'll also use a real-life example, which is this fluorescent protein called amiosphere-B. And this has a chromophore in the center, which is depicted here in yellow. And when you illuminate this protein, this chromophore undergoes a cis-trans isomerization and also several residues in the surroundings of this chromophore undergo conformational changes. And these conformational changes are pretty large. However, if we crystallize the protein and we illuminate the crystals, we can collect diffraction data and calculate an electron density map, which clearly shows the reference state, but there's hardly a sign of our triggered state. So this is a very nice case to be solved with Xtrapol8. So the main tools that Xtrapol8 will give you to get to your triggered state structure is the Bayesian-weighted Fourier difference electron density map and extrapolated structure factor amplitudes. And it will calculate those with the following input. So you need to give Xtrapol8 a reference X-ray diffraction data set. You also need to give it a reference structural model. So this has ideally be refined in our reference X-ray diffraction data set. And then you also need a triggered X-ray diffraction data set. So this is data that has been collected on a crystal or crystals that contain this low occupancy state. So the first one, this Bayesian weighted Fourier difference electron density map, is a big name for actually not such a difficult thing. So what we do is we just subtract the reference X-ray diffraction data from the triggered X-ray diffraction data. Of course, we do this with the structure factors. So you get FOPS triggered minus FOPS reference. And then we multiply by this Bayesian statistics weight factor to to reduce uncertainties. Then we get these different structure factor term, which we can then combine with the phases of our reference model to calculate a difference map. And that's the Fourier difference electron density map. This is a difference map, so it can be interpreted as any regular difference map. So this means that negative peaks, so they're shown here in red, they refer they show actually features that disappear in our triggered state, while positive peaks, so here in green, they point to features that appear in our triggered state as compared to the reference state. So then we also calculate extrapolated structure factor amplitudes. And these are structure factor amplitudes which we mimic those structure factor amplitudes as if we were collecting on crystals with a full occupancy of our triggered state. And we do this by taking the different structure factor term from our previous slide, multiply by a factor alpha, which is the extrapolation factor and is related to the occupancy. And then we add the reference structure factors again. Now, these structure factor amplitudes mimic normal structure factor amplitudes, and it means that we can use them in reciprocal space refinement, and we can also use them to calculate electron density maps to do some real space refinement. So what you see here on the left is the equivalent of a standard 2FOFC map, and on the right is the equivalent of a standard FOFC map, where we just replaced the observed structure factor amplitudes by the extrapolated structure factor amplitudes. So very briefly, this is what Xtrapol8 does for you to help you to get you to your triggered state. So now I'll explain a bit about how to use Xtrapol8. So there are different steps in the Xtrapol8 pipeline. So let's start with the first one, which is importing the data. So when you open the Xtrapol8 graphical user interface, you'll get the first step, which is input-output, where you can give this input data that we talked about before. So a reference X-ray diffraction dataset, a structural model, and a triggered X-ray diffraction dataset. If you have any ligands, you will also have to provide a CIF file as you would normally do for refinement. So good. Then we can go to the second tab and change some options to start running Xtrapol8. And we advise to start with Xtrapol8 in the FOFO only mode. So this is a mode of Xtrapol8 where we only do a small part of the Xtrapol8 pipeline. So we'll calculate, Fourier difference electron density map, which we then analyze using the Map Explorer tool. So remember that this Fourier difference maps shows actually the unbiased difference between our triggered and our reference state. And we try to automate the analysis a bit with the Map Explorer tool, which will integrate these difference map peaks and assign them to residues. So what you get out of this is different files and a figure, which shows the amino acid sequence here on the x-axis. You get some annotations of secondary structures, such as beta sheets and then alpha helices. And on top of that, then you see the peak integrations of your difference maps, so positive peaks and negative peaks on your specific locations. So you get that for your protein chain, but also for ligands or water molecules. So for example, the big negative peak that you see over here shows this big negative peak that we see on our chromophore. And so this is your first run of Xtrapol8. It only takes a few minutes. And then it's up to you to look at the results. So what do you need to look at? Well, there's different graphs that we provide. So you have, for example, a graph that shows the isomorphism between your two data sets. So what you ideally want is, when we look at the red curve here, which shows the R iso value, you want this to be low at low resolution, and then you want a smooth increase at high resolutions. And it might indicate that you might need to cut your resolution at a certain point if this gets wobbly or if your data gets too non-isomorphous at high resolution. And then you also get this Map Explorer plot, which you can use together with looking at the map in COOD. So what you want is you want to have specific peaks on specific residues that do make sense. So if you have peaks all over the place, you might want to change the RMSD levels and so on to get to the most relevant peaks. So if you're done with looking at that, you can start playing with your parameters. So you can change, for example, resolution. Then you can also change the Bayesian weighting scheme. So we have 3 kinds of weighting schemes. We have Q weighting, K weighting, and no weighting. You can also change scaling parameters, and you can also change the parameters of the Map Explorer tool to use only the most relevant peaks in your maps. So I do not have time to go into the details about K weighting and Q weighting. But these are the weighting schemes that were introduced by Ushby and Bourgeois in '97, and a few years later by the group of Keith Moffat in 2001. And they improve your maps really a lot. So if you're done with playing a bit with those parameters and finding which set of parameters is best for you to calculate these FO only maps, you can go to the second step and you can run Xtrapolate in the fast and furious mode. So in the fast and furious mode, we'll add a few steps to our Xtrapolate pipeline. But important to know is that as a user, you only have a limited parameter choice. So there will be a lot of parameters that will keep their default values. And this is because we want that in this mode, Xtrapolate keeps on running very fast, but it will make you make a bit furious because you cannot change everything. So in this mode, in addition to the calculation of a Fourier difference electron density map, we will also calculate extrapolated structure factor amplitudes and the extrapolated maps, which we then also analyze using the Map Explorer tool, which will allow us to estimate the occupancy and then refine the structure. So I'll explain a bit more about this. So recall that for the calculation of the extrapolated structure factor amplitudes, we used this formula over here, where we multiply our difference structure factor term with this factor alpha, and we add the reference structure factors again. However, we actually don't know this alpha value because we don't know the occupancy of the triggered state in the crystals. So what we'll do is we'll calculate extrapolated structure factor amplitudes for many different alpha values. So for many different possible occupancies of that triggered state. And with those extrapolated structure factor amplitudes, we can then calculate these extrapolated maps all for different alpha values. And this will help us to estimate this true or this best alpha value for your data set. You might have noticed that our Fourier difference electron density map resembles those extrapolated difference maps quite a lot. And the resemblance is highest when we look at the extrapolated difference map, which is calculated at the best alpha value. And we'll use this to estimate this alpha value. So we have actually 2 what we call difference map submethods. So in the first one, we'll try to find the locations using the Map Explorer tool. We try to find the locations of the peaks in our Fourier difference map, and we'll then search for those maps that have the highest signal on those same locations. And then secondly, we calculate the correlation coefficient between the Fourier difference maps and the extrapolated difference maps. And if we plot those, we should find a value, a maximum, which is hopefully the same for the 2 methods to get your best alpha value. So now that we have found our best alpha value, we know what would be our best set of extrapolated structure factor amplitudes, and we can do some refinement. So there is a bit of automatic refinement done within Xtrapolate. So we first do some real space refinement using the reference model in our initial extrapolated map. We'll also do some reciprocal space refinement using our reference model in our extrapolated structure factor amplitudes, of which we can then use the results again in some real space refinement. And with this, our first fast and furious run is finished, and it means it's back to the user. So again, you have to do the same things. So look at the graphs, look at the maps. So for example, of graphs, we already just saw the results of this alpha estimation. So what you want to see is a clear peak, with this, you might want to change the occupancy range that you want to test. There's also other graphs, such as here, showing the signal and the sigma values for the different occupancies. And this might, again, give you an indication that you might want to change your resolution range. And again, also look at all the different maps. And if you're done with that, you can start playing with the parameters again. So you can change the occupancy range. You can, again, change your map explorer parameters. And you can also change some refinement parameters. For the refinement, the user has the possibility to choose the Phoenix or the CSP4 route. So if you use Phoenix, you will do the reciprocal space refinement with Phoenix refine and the real space refinement with Phoenix real space refine. And if you use a CSP4 route, you will use RefMac and COOD for the two refinements. And in each of the two routes, we have selected a set of parameters that we think are useful to change when you refine in extrapolated structure factor amplitudes. So if you're done with that, you can maybe go all the way in the calm and curious mode. Now, the calm and curious mode looks very similar to the fast and furious mode, but there are two main differences. And the first one is that you now have the possibility to change all the parameters within Xtrapolate. So you can, again, change your Bayesian weighting schemes. You can select different strategies to calculate extrapolated structure factor amplitudes, and so on. You can actually just change everything if you want. And secondly, we will not refine at the best alpha value, but we will refine our structure in all the extrapolated structure factor amplitudes. It means that we will refine for all the different alpha values. So that's why this mode is called a bit calm, because it will take a bit longer, but it's more curious because the results of these refinements can then be used to estimate the occupancy, so to estimate this alpha value in an additional way. So let's have a look at these two green steps. We'll refine the model in all the extrapolated structure factor amplitudes, and this means that we will get models for each alpha value. Now, if you look close at those models, you will see that they start evolving from our initial state, for our reference state, towards our triggered state with increasing alpha value. And then it will stagnate because we're doing a restrained refinement and we'll just inflate the difference and get more noise, so the model will not change anymore. That means that if we plot all the interatomic distances in function of alpha, we get this steady increase, and then we reach a plateau value, and it's at this plateau value that we estimate alpha. So these two steps are actually additional in the calm and curious mode, and again, it's up to the user. Look at your results, look at all the graphs, look at all the maps, and this can be a lot depending on what you ask Xtrapolate to do. Nevertheless, you ask Xtrapolate to do it for a certain reason, so you have to look at the results. So if you ask it to calculate extrapolated structure factor amplitudes with different strategies, well, you get results for all of them, and you can see that are probably differences between them, and you might want to select a specific strategy based on that. And again, you want to play with different parameters. So like I said before, you can again change the Bayesian weighting scheme. You can also change the extrapolation strategy. So we have 9 different strategies, and you can run them actually all 9 at once. We also have parameters for negatives and missing, and again, you can change your refinement parameters because, well, if you want this distance method to work well for your alpha estimation, well, you need to have well-refined models. And so the message what I want to say is that while Xtrapolate is an automatic tool for you to get to that low occupancy state, it's very important that you look at the results and play with the parameters, because there's not one set of parameters that will work well for all different cases. And I quickly want to illustrate that with a easy looking example, or at least at first glance. So the colors have changed a bit. So this is also a different model. It's unpublished. So we have our reference model here in gray, and we have our Fourier difference map here in orange, which just covers these three atoms. So if you then want to know the occupancy of this decarboxylated state, we run Xtrapolate and use the difference map method to get to estimate the alpha value. But what we get is that the two methods actually give a completely different answer. And if we look into what's probably the most reasonable region for alpha values, we basically get a flat line for both methods. And this can be understood if we look at the extrapolated difference maps. So what you see here are the extrapolated difference maps, so the Fextrapolated minus Fcalc maps, all at the same sigma value, but for different alpha values. And as you can see, they're basically all the same. So from this, it kind of makes sense that we see that our difference map methods, they're not sensitive to just determine the occupancy based on these three atoms. But what have we learned during this presentation? Well, you have to look at the maps and look at all your results. So we looked at the difference maps. We understand why this alpha determination is not sensitive using these difference maps. But we still can have a look at our extrapolated maps, our refined maps, and ask ourselves questions like, does the result make sense? Do we still see the reference state? And can we interpret the data and do this for all different extrapolation strategies? So when we look at the normal extrapolated maps, so the 2F extrapolated minus Fcalc maps, we can see that at low alpha values, so if we don't extrapolate too much, we still see our reference state, and we see that the density for that reference state is disappearing with increasing alpha values. And so in this case, this could help me to estimate that alpha value actually on a manual basis. And just a little spoiler alert, we are, of course, working on the incorporation of a method that also takes these maps into account, so that in a future version, the user don't have to estimate this manually, visually. But this is just a case to show that it's very important to look at your results before you start interpreting the results of your extrapolated model. So more information about Xtrapolate can be found on our GitHub page, where you find information, where you find the link to the publication. You also find a manual for the command line and the graphical user interface, and information about installation, usage, the output files that you get, and good practices to follow. And you can also find our contact information. So if you have a question, if you need some help, if you want to report a bug, if there's something missing, please contact us so that we can help you further. Xtrapolate is, of course, developed by many different people, and in particular, I want to thank Jacques-Philippe Colletier, Nicolas Coquel, and Thomas Barens. And I also want to thank all the Xtrapolate users that came with very useful feedback. And then, very importantly, Xtrapolate is built on existing software, being CCTBX, Phoenix, CCP4, and Qt. So this is just a little call that if you use Xtrapolate, please cite us, but also refer to these software which are also run when you run Xtrapolate. And just to finish, I want to say that we have some postdoc positions open in our group. So if you want to do time results crystallography, please contact me as well. Thank you very much.
Very much, excellent talk, really fantastic stuff. And also we can see how new software comes to the suite with this, because that's one of the things that we're discussing, whether we want this software. So as a call, anyone who has software thinks that's interesting to be also, you know, distributed by CCP4, just talk to the chairs, and they will be very happy to discuss these issues. Is there other questions? Is it Martin Marley from Southampton?
Thank you, Ivo from Southampton. I would like to ask you, what's your favorite Bayesian weighting scheme? How, as a user, should decide which scheme I should use? And another question, I'm sorry, maybe it's not a nice question, but how to avoid watching my results like false positives results, because sometimes maybe using I can make some model bias on my results, so then I will just see what I want to see. How to avoid that?
Yes, so for the first question, which weighting scheme is best, we found that when your occupancy is quite high, and here we talk about 20-30%, Q weighting might be better. And if the occupancy goes rather low, like below 10%, K weighting might be better. And let me check, do I have... maybe here. Yeah. With this K weighting, you also have an additional scale factor, which you also want to change, but I really have to go into the mathematics here to show you what this scale factor does. So yeah, basically Q weighting would normally work, but it might be that the K weighting gives you better results. And so that's why I say it's really depending from a case-to-case basis. And yeah, you have to look at your maps to see which one works best. And it might even be that for the Fourier difference maps, you want a different weighting scheme than for your extrapolated structure factor amplitudes. And then for your second question about how to avoid model bias, well, that's why in the Fourier difference map, we just use the phases of your reference model. So we don't use an already triggered model, which means that if you're biased, you're rather biased towards your reference model, which I think is more safe than getting some kind of interpretation, which is just based on a bias of a triggered model. We also extrapolate just the amplitudes. We do not try to extrapolate the full structure factors with including phases, because that would indeed be a big trap for model bias towards a triggered state that you want, and maybe it's not in the data.
Okay, we got a question on Slack, I think.
Yeah, there's quite a few, so you might have to answer some after. But the first one that came in was from Yahui, I think. We often see crystals have different levels of ligand or fragment occupancies. Can they be used as reference and triggered input data in Xtrapol8?
So the question is whether you can use it for ligands or...
I didn't quite understand that question. So it's about
if you have
different occupancies of fragments, I think.
Yeah, so if we have different levels of ligands or fragment occupancies, can they be used as reference and triggered?
Oh, yes. Actually, yes. So I'm saying that your reference data set is comes from a crystal which is fully in the reference state. But actually, it can just be two states which are different. So in essence, yes, it would work. But if you have one with a very low occupancy and one with a bit higher occupancy, if you take the difference, you should still see that. Of course, it will be less sensitive than if you start from a true reference state.
Maybe one more question.
One more. Okay. James Holton asks, is your M the same M found in sigma, as in 2MFO DFC maps?
Oh, yes. So these are the standard figure of merit to calculate maps. And I'm happy to discuss further with James Holton if he has better ideas.
Questions more on Slack you can answer afterwards. Is there one more in the room? Otherwise, thank you very much.
Thank you.